Welcome everyone, I'm András Imolay and I'm going to talk about Matroid products via submodular coupling. This is joint work with Bérczi, Gehér, Lovász, Maga and Schwarcz. First, I will define Matroid. So the Matroid is a pair. It is given a ground set S and also a family of subsets of this S, which we call independent sets. And we call this pair a matroid if it satisfies the independence axiom. That is, the empty set is independent, the independent sets are downward closed, and the most important property is that if we have a smaller independent set and a larger independent set, then there exists an element from the larger independent set that if we add this element to the smaller one, it is still independent. Maybe the two most important examples are linear matroids and graphic matroids. A linear matroid is given by a finite set of vectors from a vector space as ground set, and the independent sets are the ones that are independent in the linear algebraic sense. And also we call a matroid linear or representable over a field if there exists a finite set of vectors over a vector space over that field, such that it defines this matroid as a linear matroid. And the graphic matroid is defined on the edge set of a graph, and the set is independent if it is a forest, that is, it contains no cycles. It can be proved from the axioms that if we take any subset of the ground set, then all inclusion-wise maximal independent sets have the same cardinality. We call this the rank of X, and with this we can define the rank function, which assigns to all subset of the ground set a non-negative integers, and it can be proved that it satisfies the so-called rank axioms. That is, it takes 0 on the empty set, it is monotone, subcardinal, and most importantly, it is submodular. We will need this submodular inequality later. It says that if we take any two subsets, X and Y, then this inequality holds. An interesting thing is that we can define a matroid through the rank function. That is, if we give a function to the non-negative integers that satisfies these axioms, then it defines a matroid, and we can reconstruct the independent sets of this matroid. So it is natural in mathematics that if we have some mathematical structures, then we consider the product of them. So it's not a surprise that matroid products have been considered earlier, but there is no canonical definition from this. There are several matroid product notions earlier from the literature. One of them, so I will talk about the three most important ones. One is the quasi-product. So all of these matroid products lives on the product set of the ground set. So one of them is the quasi-product that we call a matroid a quasi-product of two matroids if all of the horizontal sections are isomorphic to M2 and all of the vertical sections are isomorphic to M1. A stronger notion called product is when we require that if we take any set X and any set Y, then their product, so this purple rectangle is flat if X and Y was flat. Well, I didn't define flat, but I don't want to go into the details because we don't need this. And maybe the most natural and the strongest notion is the tensor product. That is, if we take any two subsets X and Y, then the rectangle that define the rank of the product matroid should be the product of the ranks. So what do we know about this matroid product? Lovász and Mason proved that any two matroids admit a product, but it remained open whether a tensor product always exists. And for representable matroids, it's easy to see that actually this is the case. So if we have two matroids that can be represented over the same field, then we can define the tensor product in the linear algebraic sense, and it's easy to prove that it actually gives a tensor product in this matroid theoretic sense as well. But it turned out, Schwarcz proved that there are matroids that do not have a tensor product, The Vamos matroid is the smallest matroid that is not representable over any field, and this U23 is a uniform matroid over 3 elements, which has all of their subsets is independent except for the whole set. So our main contribution is defining a new notion we call coupling. This is a new kind of matroid product, and the motivation comes from probability theory. So in probability theory, if we have two probability measures, mu1 and mu2, then we call mu a coupling if their marginals are mu1 and mu2. That is these horizontal and vertical rectangles. I will call these rectangles later full rectangles. So on these subsets, the rank is equal to mu1x and mu2y that you can see here. And without going into the details, I just want to mention that this is actually an extremely important notion in probability theory with plenty of applications. Note that actually we didn't really use anything about mu1 and mu2 being measures. So taking any two set functions, we can define coupling in a similar manner. That is we call on the product space. So on the product of the ground set, a set function coupling. If for any of these full rectangles, the rank of the coupling is equal to the product of the ranks. This is just the same as the probability measure case, except when we talked about probability measure, the whole sets always had measure 1, and here it might not be true. That's why we need these phi1s1 and phi2s2 products. Okay, so some motivation about this. In recent years, it turned out that tropical geometry has a connection with matroid products, and hence they started to consider matroid products in this totally different point of view. Also, extended formulation is a really important notion in combinatorial optimization, which is something like that we have a polytope and we extend it to higher dimension to take and want to extend it such a way that we get a polytope that has easier description in some sense, and couplings are also can be considered as a really similar kind of extension, but it's a bit different. And finally, our main motivation comes from the aim to build a limit theory for matroids, but I will tell this a bit more detail later. Okay, so back to couplings. So as we have seen, the definition of tensor product and coupling is really different. So we prescribe the rank on some rectangles, but tensor product is stronger because there we prescribe it for all these rectangles, and couplings we only these full rectangles that has one side equal to the whole ground set. And we have already seen that tensor product does not always exist. So it is a natural question whether coupling always exists. And our main result is that we prove that any two matroids admit a matroid coupling. That is, if we take the rank function of two matroids, then there is a rank function that is a coupling of them. So quickly, let's go through the main ideas of the proof. So we take two bases, that is maximal independent sets in M1 and M2, and we define this function phi. So let's understand this. This just says that first we look at all the horizontal sections and take their rank with respect to the second matroid and add them up. And then in the similar way, we look at all the vertical sections that is in B2 and add up the ranks with respect to the first matroid. And finally, we subtract the intersection with this B1 times B2. And just a remark that these elements that are not on the rectangle of B1 and B2, these are loops. That is, they will have rank 0. So if they look at them, this definition gives that the phi value of any subset of this is 0. So these are going to be loops at the Matroid. And so yeah, this is almost the solution. So this satisfies almost all the properties we want, except that this won't be monotone. So to obtain the final rank function of a Matroid, we have to monotonize this and have to prove that it still works. It looks like that this construction is not canonical, as we had to choose 2 bases arbitrarily at the beginning. And also, you should somehow expect that if we have loopless Matroids, then their coupling should also be loopless. But it turned out that there is not always such couplings, because we proved that if a coupling has no loops, then it is actually a tensor product. So the Vamos Matroid and the uniform Matroid we've seen earlier, they have no tensor product, but they have coupling, and all of their couplings necessarily have loops. Okay, and some more, we generalize this theorem to other kind of set functions. First, for K polymatroid. K polymatroid is almost the same as the Matroid rank function, except for the third axiom. So it's not subcardinal, but the cardinality times K bounds the function value. And for a K1 polymatroid function, the K2 polymatroid function, there exists a K1 times K2 polymatroid coupling. And also in polymatroids, we don't necessarily assume that they are integer valued, but if they are, then the coupling is also integer. It can be found an integer valued coupling. And even in a more general setting, so if we take any polymatroid function, that is a function that is polymatroid for some K on measurable spaces, so not even necessarily finite ground sets, they still admit polymatroid coupling. Okay, our next topic is tensor product. We consider tensor products as well, and it turned out that it has a strong connection with representability of Matroids. Ingleton proved that the rank function of any linear Matroid satisfies this. Well, it first looks like some unnatural inequality, but this is actually a really important inequality. And for example, the Vamos Matroid doesn't satisfy this inequality. That's why it cannot be representable over any field. Some remarks is that it can be decided whether a Matroid is regular, where regular means that it is representable over every field, but most of the questions are undecidable. So for example, deciding whether a Matroid is representable over a specific field or over fields with a given characteristic or over any field is hard. And that's why we cannot expect such a characterization. But for example, we can describe the linear Matroids with these kinds of inequalities. And there is a lot of research behind this. What's the connection with tensor product? Well, so as we have seen, in the linear algebraic sense, there is a tensor product, and this U2-free uniform Matroid is representable over every field. So the existence of a tensor product with this Matroid is a necessary condition for linearity. And what we proved is that if we have a submodular function and that has a tensor product with the rank function of this uniform Matroid, then the Ingleton's inequality holds. More specifically, if they have a submodular tensor product, then Ingleton's inequality holds for pairwise disjoint sets. And if it is actually an increasing, so it's a polymatroid tensor product, then the Ingleton's inequality holds for all 4 subsets. And this, for example, a trivial corollary of this is that the Vamos Matroid and U2-free has no tensor product because the Vamos Matroid doesn't satisfies Ingleton's inequality. And finally, some words about universal functions. First, I want to define the notion of a quotient. So if we have a submodular set function and take any partition of the ground set into Q pieces, then the quotient can be obtained by contracting these pieces into points and only look at the function on these sets, that is the union of these partition classes. And so this is a really important notion for the limit theory of Matroid, because there is a definition of convergence of submodular set functions that is defined through these quotients of those submodular set functions. And an important remark is that if we take phi1 and phi2 and the coupling phi of them, then the partition corresponding to the rows actually gives a coupling. Sorry, so it's if we look at the quotient with respect to these rows, then we get back to the first function, except with some multiplicative constant. And also, if we look at the partition corresponding to the columns, then the quotient with respect to this is the second function. And actually, this was our main motivation why we started to examine these couplings, because we wanted to find this kind of a common lift. That is, if we have two submodular functions, we wanted to find another submodular function that has a quotient, both of. So both of them is a quotient of this submodular function. But even more generally, a universal function is a function that contains all finite normalized function as a quotient with respect to some property P. This is some general framework. With properties, we mean something like submodular or monotone. So these kind of properties of set functions. And we proved that under some technical conditions, this finitely closed, extendable, liftable, and p-bounded, if the property has these properties, then there exists a universal set function. Here, I just want to remark that liftable means that any two set functions with property p has a common lift, and and we prove this. So a consequence of this is that there exists a universal increasing submodular set function, and to prove the liftability of this property, the increasing submodular property, we needed the coupling, that any two increasing submodular functions have a coupling. And also another corollary is that there exists a universal coverage function. I don't want to go into the detail of what is a coverage function, but it's a really important notion in combinatorial optimization. Finally, I just want to sum it up. So we introduced the notion of coupling and proved that any two matroid and polymatroid functions and submodular functions with a coupling. We built a connection between tensor products and representability, and also we proved the existence of universal subfunctions with respect to certain properties. And I will close the talk with some open problems. So, for example, our theorem does not imply anything about the existence of a universal function for b-bounded submodular functions. Here, b-bounded just means that bounded by some number b. So we could only prove that increasing submodular functions have a universal function, but for general b-bounded, we don't know and doesn't have a counterexample as well. And also, it would be really interesting to clarify the connection between representability and tensor products. Maybe even just the tensor products with these uniform matroids can somehow characterize the representability of matroids. That's all I want to say. Thank you for your attention.